Okay, in this video we're going to be talking about exponential functions to start with, and then we're going to work and look at what their derivatives are. So let's look at a basic exponential function. So we're going to have the simplest, we'll look at the simplest function first. Y is just equal to a to the power of x. So x is going to be our variable, obviously, because it's going to keep changing. In this case, a needs to be greater than 0, and a can also not equal 1. The reason it can't equal 1 is because 1 times 1 times 1 times 1 to it's 1 to the power of any number is just 1, so it can't equal 1. So that's our simplest form. What's the general function look like? Well, it looks something like this. We've got y is equal to k times a to the power of x minus c plus b. Now this plus b is also a to the power of x minus c, everything plus b. And what each of these is going to do, and we'll talk through it. So also for this, a needs to be greater than 0. A again can't equal 1, and also this time k cannot equal 0. The reason being it can't equal 0 is because otherwise we've just got b just as a constant function. We can't actually have 0 times a to the power of x minus c, because that doesn't, it kind of negates the whole exponential functions that we're talking about. Alright, so what does a, c and b do in the case of these? Well, a is just how fast or how steeply the graph increases or decreases. B controls the vertical translation, and C controls the horizontal translation. So remember, V will change how much when the graph's moving up and down, C will change it left to right. So, and obviously our horizontal asymptote is B, because we can't actually have this being equal to 0, so that means that there's got to be a vertical asymptote at B, because this, whilst it will get incredibly small, it will never equal 0, so B is our vertical asymptote. So if we have a look, there's a couple of cases that I want to look at, and then we'll jump into an example of how we might graph it and talk about its domain and range. So if we've got k being greater than 0 and a is greater than 1, the function, in this case f of x, we'll just call it f of x for a function, is increasing. So that means it's going to look something a bit like that. If k is less than 0 and a is greater than 1, that's a really bad greater than sign, that's a bit better, then f of x is going to be decreasing. which case the graph is going to look something a little bit like that. It's going to hit the ground. What if we've got k greater than 0 and a being somewhere in the region between 0, that's the a, and 1. So a is somewhere between 0 and 1. What f of x is going to be in this case? Again, it's going to be decreasing, but it's going to look like this instead. So here, where a was greater than 1, it was decreasing, but it was sort of in that kind of shape. When a is between 0 and 1, it's still decreasing, but it's in that kind of shape, so it's the opposite. What if we've got k being less than 0, but again between, a is somewhere between 0 and 1? Well, it's going to be increasing. We've got increasing, decreasing, decreasing. Kind of makes sense that it's going to be increasing again. And it's going to look a little bit like that. So again, it's a slightly different shape. If you think about it, they're kind of mirror images of one another, even though I can't draw mirror images. So, but think about it. This one here is, these two are just mirror images of each other. This one and this one are also mirror images of each other. If you were to stick a mirror in there, that's what this one would look like. Again, if you were to stick a mirror in there, that's what this one would look like. Alright, so that's our general rules for exponential functions. Let's have a look at an example. So, what if we have this formula? And let's close this section off. What if we've got a formula that looks something like this? We've got y is equal to 3 to the power of x plus 1. What's this going to look like? Well, we're going to have a horizontal asymptote at 1. So if we were to kind of sketch this out a little bit. Something like that. We're going to have, let's pick a different colour. Let's go red, because red's danger. We're going to have somewhere along here that's going to be where y is equal to 1. So the graph can't cross over that point. Where is it going to cross our y-axis? So what does y equal when x is equal to 3? When x is equal to 0. So remember from our indices laws that any number to the power of 0 is going to be 1. So it doesn't matter if it's 3 to the power of 0, it's just 1. 10 to the power of 0 is still just 1. So if x is equal to 0, then y is going to be equal to 1 plus 1, which is just 2. So let's keep using red for the moment. So in here, where y is equal to 2, the graph is going to go through this point. Now, we don't know yet which way it's going to look like, but let's look at this. So, if we were to break this down, C we don't have. C in this case is just 0. So, we've got A, B, C, and K. Well, K in this case is just 3, so it's greater than 0. A is a positive number, so it's got to be somewhere in here. So, and B is just plus 1. So we've got that. It's going to, in fact, look a little bit like this. I'll try and draw it, but I can't make any nice promises. Excuse a little bit of a hiccup there. So it's going to be increasing. So we could, if we wanted to, get a few extra points. And why don't we do that? So I kind of skipped it a little bit ahead. This is what it looks like. But if we really wanted to know exactly what the graph looks like, well, we need to get a few points. So let's substitute in some values for x. So what about when x is equal to 2? If x is equal to 2, what does y equal? Well, y is going to be 3 to the power of x, which is 3 to the power of 2, plus 1. And that, 3 times 3 is just 9, plus 1 is just 10. What if x was equal to minus 2? What's it going to be this time? Well, let's have a look. We're going to have 3 to the power of minus 2 plus 1. Well, we know from our derivatives that we've been doing that this is just going to be 1 over 3 to the power of 2 plus 1. All of this is going to equal 10 over 9. Now the reason it's 10 over 9 because 3, so if we wanted to, let's write this out. So 1 over 3 squared is 9 plus 1, but 1 is just 1 over 1. We need to cross multiply or find the lowest common denominator of these two fractions in order to add them together. Now the easiest, most simplest way to do that is to what we call cross multiply. So let's grab it out a different colour. Go yellow. So cross multiply means we go 9 times this. So each one of these yellow lines is a multiplier. So this is going to be 1 times 1 plus 9 times 1 over 9 times 1. So 9 times 1 is our denominator. Our numerators are going to be 1 times 1 and 9 times 1. And that is just 10 over 9. And that's our answer. So if we want to graph this, we could say that 10 over 9 is just above, and we're talking just above 1. So if we want to, it's really equal to 1 and a ninth. So we know that somewhere down here, where x is equal to minus 2, let's just say it here, that this point here is 10 on 9. And similarly, we know that when x is equal to 2, let's try and get it somewhere right here, 2, that up here, y is equal to 10. And we've got then 3 points that we can graph it with, so we know that this one starts up here and then it goes down here, but it cannot cross this line here because we can never actually get our exponential here to equal 0. So So what's the range and domain of this function? Well, the domain, if you remember, is just x values. And range is y values. So let's look at what values of x can this have. Well, we don't know how far off this side it goes. Eventually there'd be a point where it would be just continually to increase for very little x. But along this way, we know it's going to keep going forever, because we'll never actually hit this y equals 1. So we could say that the domain of x, excuse my squiggly bracket because I'm really bad at drawing them, that x is any real number. Now, I tend to write them like that. There are other ways to write them as well. So what about the values for, what about the range for y? So y in this case, it can't be anything less than 1. And it also can't be equal to 1. We know that it can't be equal to 1, and it can't be less than 1. So it's always going to be greater than 1. And that's our domain and range. So what about derivatives of exponential functions? Let's talk about those. So I'm going to, I'll save this. Alright, so let's look at some examples. Now, I've already drawn them up, so what I want to do is just talk through them. Might save a little bit of time. So, what we've found is that, let's get rid of that one. We've got this function f of x is equal to b to the power of x. So it could be a, could be b, could be any number. What we find is that our derivative of it, and if you want to look through the proof of this, it's on page 45 in the textbook, so let's write that in. Proof on page 45, if you're interested in it. What this is going to be is the derivative of a function, or derivative of this function, when x is equal to 0. So any number to the power of 0 is just 1 though. So all of this is really just, the derivative is just going to be b to the power of x, or 1 times b to the power of x. And as I said, the proof for this using limits is on page 45. Have a look through, see what you think. If you've got any questions, ask. Or ask me and I'll go through it in more detail. So what we get, if we look at limits, and we've got this number n, as n gets closer and closer to infinity, remember for limits that we normally have h tends towards 0, but in this case as n gets larger and larger and larger, what we find is that this number, or what this becomes, is a number that's very close, or getting more and more closer to 2.718281, etc, etc, etc. It's an irrational number, it's like pi, it goes on forever. Speaking of which, we've got this symbol for pi. We actually have a symbol for this number here, and we call it e. Now e is not exponent, it's just e, so the number e. So if you ever hear somebody mention, oh yeah, the number e, it can roughly be equated to 2.7, etc, etc. So what we have is, if we've got a function, f of x is equal to e to the power of x, then the derivative of it is simply e to the power of x. So, but e to the power of x is equal to just e to the derivative of it is e to the power of x. It's exactly the same. So remember, from up here, f0 is just 1. But what if, and I dare say you're not going to get a function where you just have to, what is the derivative of e to the power of x? It's going to be more complicated than that. And that's why we go through this here. So if we've got e to the power of some function, f of x, the derivative of it, so here's a function, the derivative of the function is e to the power of f of x, like it has been, but we multiply it by the derivative of the function. So if we've got over here, we've got e to the power of 2x plus 3, so e is to the power of all of this. Well, let's go e to the power of u, where u is equal to 2x plus 3, where the derivative of this is just 2. So it's really e to the power of u times the derivative of u, or u dash. So our function is going to be 2 e to the power of 2x plus 3. So we put the 2, multiply all of this e to the power of 2x plus 3 by 2. Let's look at some more examples. So we've got here 2 e to the power of x plus 3 e to the power of minus 3x. So let's work out what's our derivative of e to the power of x. Well, it's just e to the power of x. X in this case, what's the derivative of x? It's just 1. So e to the power of x times that derivative, or the derivative of x is just e to the power of x, but we still had this 2 here, so it's 2 e to the power of x is our derivative. This next one's a little bit different, because we've got e to the power of minus 3x. What is the derivative of minus 3x? Well, it's minus 3. So we've got, going to have, using this, e to the power of minus 3x times minus 3. Hence why we have this one here. So that's just the derivative of that one plus the derivative of this one. What about if we have something like x squared times e to the power of minus x? So x squared times e to the power of minus x. Well, we're going to use our product rule, because just think about it, it's two functions multiplied together. So what is our derivative if we wanted to split it up with our u's and v's? Well, in this case, u is equal to x squared and u dash just equal to 2. V is equal to e to the power of minus x, and v dash is just equal to minus e to the power of minus x. Now, why is it minus e to the power of minus x? Well, the derivative of minus x is just minus 1. Hence why we've got this minus e to the power of minus x. So let's look at it. 2, it really should be 2x, not just 2. 2x e to the power of minus x. So the derivative of x squared is 2x times by e to the power of x plus x squared times the derivative of e to the minus x, which is e to the power of minus x, all multiplied by minus 1, which is going to be equal to 2x e to the power of minus x take x squared e to the power of minus x. So all that this has done here is change the sign. Alright, so if that is our product rule, what about our quotient rule? And this is our quotient rule here. So we're going to have e to the power of 2x divided by x. So let's use our u's and v's and work it all out. So u, in this case, we're going to have e to the power of 2x. U dash is e to the power of 2x multiplied by the derivative of 2x, which is 2. So all of this becomes 2 to the power of 2 e to the power of 2x. V is just equal to x, and v dash is just the derivative of x, which is just 1. So we plug all of our values in. So we've got 2e to the power of 2x times x, take away e to the power of 2x times 1. So we've got our u dash v take u v dash divided by v squared, which in this case is just x squared. Now we've got 2e to the power of 2x terms here that we can now take out. So why don't we take those out and simplify it? So we're going to have e to the power of 2x times 2x, because we've got 2 e to the power of 2x times x, so we could rewrite this as 2x e to the power of 2x, take e to the power of 2x, which is just 1, if we take a factor of e to the power of 2x out. And this is our answer. So hopefully that makes a little bit of sense for working out derivatives of exponential functions. If you've got any questions, ask, and we can go through it again in a bit more detail. Hopefully this is making a bit of sense. If you're not quite proficient with the rules of differentiation yet, have a chat and we'll have a look at giving you some more practice at them with some extra questions. Hopefully that makes a bit of sense, and as always, thank you for watching.